a bunch of other things. But let me begin with a question that I think the answer is probably no, but if it weren't, it would be interesting. So the basic question so I'll need to define what these things are formally. Feel free to stop me at any point to ask me questions. The basic question is, so to a graph, to any graph, we associate an adjacency matrix and also a non-backtracking walk matrix. Often people use B sub G, which is a non-backtracking walk matrix. And if the graph is regular, these two matrices give essentially the same information. So you'd think they're completely equivalent. But somehow in practice, when you try to work with trace methods and with a lot of other things, the non-backtracking walk matrix seems to be better. First of all, I have no idea why. I can just show you why, and in certain particular cases it does. But this is also true in what are called trace methods for random graphs. So somehow the non-backtracking walk matrix works better for trace methods. Trace methods for random graphs to show where their eigenvalues are located. The question is, A, why does it work better? And second question is there anything that works better than non-backtracking matrices? So this works better than that. The question is why? I really have no idea. The other question is there something better? So I think there are a bunch of other questions that I think about related to non-backtracking matrices. If time permits, I'll ask these other questions, but I'll. Yeah, I mean, so what I'll concretely show you is I'll show you what is known as the Broder-Shamir trace method, which is the first trace method to prove that random deregular graphs have good eigenvalues. And I'll show you that if you do the trace method on the adjacency matrix and then draw conclusions, or you do the trace method on the non-backtracking walk, draw conclusions and convert that into adjacency information, this one's better. And it would be nice to know if there's something better. This might be a little bit in the spirit of the question of, yesterday's talk. Is there a, for Boltzmann distributions, is there some kind of thing that commutes with convolution other than sort of the natural things? But there are other questions of this form where somehow the non-backtracking matrix, even though it conveys the same information, does things better. And I'll give another example, which is, I hate to mention it, it's probably a fairly difficult problem. There's something about it sort of also works better when you study the so-called Moore bound. which is a question about the girth of deregular graphs. This one hasn't really budged by more than an additive constant since the 1950s. So this maybe is a little more difficult than this question, but we'll see what we get to. For the more bound, the question is simply, I'll state it, the question, but just to give you a sense of where we're going. Okay, so let me define these formally. So, a graph you can think of as having vertices and edges. That's the simplest way, although we'll allow multiple edges and self loops. So we'll allow multiple edges and self loops. In particular, when I'm describing why the non-backtracking matrix works better, we want a model of a random graph. So I'll give you a model of a random deregular graph. And most of what I'll be doing is from the paper of Broder-Shamir that kind of started off trace methods. So this goes back to sort of Broder-Shamir. I believe this is 88 in a Fox proceeding. And it's called the permutation model. So you have D is even. You can make similar models and D is odd. You take N, which will be the number of vertices of the graph. And you take D over 2 permutations. So permutations on the set 1 through N on the set integers 1 through N. And you simply take D over 2 uniformly chosen independent random permutations. A permutation might look like it takes 1 to 3 to 7 to 2 back to 1, and then maybe it has, it could even have a vertex that it takes back to itself, and so on. And you think of each one of these as giving you a 2-regular graph. So you think of this as being an oriented edge, but it also has an edge in the other direction. So each permutation gives sort of a 2-regular graph. And then you superimpose them to get a deregular graph. On N vertices. And I'll call this model G. I guess people are probably calling it something like G, maybe regular N comma D. There are other models of a random regular graph. This was a little bit controversial at the time of Broder and Shamir, because this, can have a self loop. You can have multiple edges. If pi1 looks like this and pi2 has an edge from maybe 1 to 3, 4 back to itself, you can get multiple edges as well. It turns out by the time I proved my theorem about what the eigenvalues of a random graph look like, this was not an issue because it had in the intervening time been proven that all the models are essentially equivalent for the type of questions that I'll ask. But let me at least state a formal question. Okay, so now we're going to talk about the eigenvalues of these graphs. So given a graph G with vertices and edges, the adjacency matrix of G, so it's a square matrix indexed on the vertices such that its UVth entry is the number of edges from U to V. So the best way to really think about a graph is it's a directed graph, which has edges going in one direction and each edge is paired with one in the opposite direction. This makes it easier for the formal definitions, but informally, you just think of it as some sort of something with vertices and edges that join pairs of vertices. Okay, and why is this thing interesting? Probably most people are. How many people have some idea why this is interesting? Maybe. How many would like a little review? I'll quickly. Right, there we go. So let me say a little bit about the adjacency matrix. So in the theory of networks, so you think of people or computer connected by the edges of a graph. So when I was a kid being taught by my dad partial differential equations, this is what you did. This is what a graph looked like. You were solving Laplace's equation, the heat equation, plus, and so on. And if you actually wanted to see these things, and computers were just coming into fashion then, you could actually, my dad couldn't, but I could because I was a kid at the time, write a computer program where you're approximating the Laplacian. And the Laplacian is just, what is the Laplacian? The Laplacian of a function u means that you look at the neighbors of your point, you take the average and you compare it to yourself. So that's the Laplacian. How does heat evolve? You look at yourself, you look at your neighboring points, and if their average is higher than you get warmer. And if they're cooler than you, so it's very intuitive. So this is kind of what I think of as a typical four regular graph. You want to make it four regular, maybe you can wrap it around or so. These are very bad as far as computer networks are concerned, for the reason that if you, I'll try a different color. If you take a grid graph like this and you cut it in about half, so if this has n nodes, so if you think of this as having n nodes or n vertices, you can get a set of roughly half the vertices. So you can get a set, a subset capital U in the vertex set of this graph, about half the vertices, let's say, such that if everyone in this network wanted to communicate with phone conversations to everyone who wasn't in here, then all the traffic would have to go along the boundary, and that would create hotspots. So in computer science, if a graph is going to be connected and you have n vertices, you need at least n minus 1 edges simply to connect them. And in a lot of computer science, you want to optimize up to a multiplicative constant. There's a quote by Richard Karp that says the only constant a theoretician cares about in their salary is the one in their salary. So to within, if you think about, a deregular graph on n vertices, as long as d is fixed, that's just a constant. You're just using a constant more than the number of edges you want. But the property that you want is that for any subset of vertices, the neighboring set, and you can measure that in terms of the edges going out or the number of vertices that are connected, should be relatively large. So if you have, roughly, n over 2 vertices, but in this set U, the boundary of U is roughly square root of n, then that's not good. So in the early papers on networks, you would see these conditions. We want that for every set of size half the vertices, there's at least 3 times as many edges coming out. And if it's a tenth, there's 10. You'd see all these crazy conditions. Like I once refereed a paper that had 3 such conditions simultaneously holding on a graph. So there's a spectral side that guarantees some amount of sort of good expansion in the sense that every subset has a certain number of neighbors. And the intuition is pretty clear. So if G is a deregular graph, let me go back to black here. If G is a deregular graph on n vertices, so its adjacency matrix A of G is n by n. It's symmetric. And it's not hard to see that the eigenvalues are between d and minus d. So if you have lambda 1 through g up to lambda n through g are the eigenvalues of the adjacency matrix, then they're all between d and minus d. So we typically order them in decreasing order up to lambda 1 through g up to lambda n through g. Lambda 1 is always equal to d. And that's simply because deregularity means that every vertex sees d other vertices. Not exactly, because we can have multiple edges and so on. But d, when you count them, really d, when you count the number of edges, or say directed edges, whose tail is a given vertex, so that the row sums and the column sums of the adjacency matrix are all equal to d. And the adjacency matrix of G. Oh, question? Yeah. They're undirected, but we're going to make them directed to define the non-backtracking matrix. So it's kind of pedagogically better to think of them as directed, but each edge has an inverse edge. Or we can take a graph and say each undirected edge, we make a directed edge in both directions. Okay, so what does this mean? This means that the adjacency matrix is the sum of its eigen values times a rank 1 matrix that represents extracting the ith part. So if so let's say vi transpose, where vi is the eigen vector associated to lambda I. And if there are multiple eigenvectors, you assume that it's an orthonormal eigenbasis, which you can do. V1 Vn orthonormal. And therefore, if you pick out the first part, you get the complete graph. Sort of. So the intuition behind all of this expander stuff and is that, what does this mean? So you have the adjacency matrix times the all ones matrix is D times the all ones matrix, all ones vector. So if you normalize this, so you divide by the square root of n to normalize. And then what that means is that the adjacency matrix, if you take this times its transpose and multiply by the eigenvector D, you get D over n times the all ones matrix. And you get, what's left over. If you think of it as sort of an error term. So what's left over is really what you have from the eigenvalues from 2 to n. Lambda I, vi transpose. And to think about this, you'd say that one way to think about this is that the L2 norm of this error term is small. So first of all, this lives on the orthogonal complement of the all ones. The second thing is that if you look at its L2 norm, how much it stretches any vector, that's going to be exactly equal to the maximum eigenvalue in absolute value. So what we do is you can define lambda of G to be the next largest eigenvalue in absolute value. And the intuition is that if all of the eigenvalues except the first were 0, you'd be in the absolute best, most interconnected possible situation, because this would be nothing. So you get a complete graph. If D is fixed and n goes to infinity, then you've got like little d over n's, which are tiny things here. So this is mostly things that kill those d over n's. And then, you have some ones in the adjacency matrix. So it's a little bit misleading to think of it in this way, because you have to realize this has a lot of minus d over n's and a few things that are close to 1. But this works. The idea of it's something plus another matrix that's bounded by the maximum absolute value of the other eigenvalues gives you results. And by the way, I can say this, please feel free to stop me at any point. I'm making errors, blatant errors, it's good to be corrected. And if you have any questions. So if you have a graph and you have, let's say, two sets of vertices, U and W, and they can overlap. Two subsets of the vertices, you can measure how many edges go from U to W and use this approximation. So the number of edges from U to W, meaning that join 2 points in the two sets, is literally, you can just take the adjacency matrix. You can take a vector that represents the characteristic vector of one times the characteristic vector of the other, and you get a reasonable estimate. So this is equal to, you take the characteristic vector of, or the indicator function of U times the adjacency matrix times the indicator function of W. And then what that means is that this part gives you sort of the expected number of edges. So this is equal to the size of U times D over N, the size of W. And then what's left over is something that's an error term. And the size of this is bounded by the projection of these indicator vectors to the orthogonal complement of the ones times the maximum largest eigenvalue. So this is less than or equal to lambda of G in absolute value, let's say, times what's essentially the norm of these vectors, except you can project to the orthogonal complement of the ones. You get something a little bit better out. You get something like the size of U times n minus U over n, and the same thing with W. And this is often called the expander mixing lemma. If you want to apply a power of the adjacency matrix so that you're really taking a number of steps in the graph, then what you're getting here will still be, the eigenvalues of the kth power, just the kth power of the eigenvalues. So then you could even, if you want to, you can put a k here, and you can put a k in the D, and then this lambda becomes a k. And then you can see that if lambda is sufficiently separated from D, and you take k large, then this term really dominates. So it's mixing in the sense of a Markov chain mixing. It tends to give you a rather not so good bound on the mixing time, but for the point of how good does one set connect to any other of a given size, this is sort of the right intuition. Okay, any questions? How many people have seen this picture? Yes. It's always good to return to this, even if you haven't. Okay. So how small can this second eigenvalue b. So not what I really want to talk about so much, but so the theorem due to Alon and Bapana says that lambda 2 of g, so lambda of g, which is the largest eigenvalue, in fact, even the second largest eigenvalue is at least as big as 2 squared of d minus 1 plus something that, as n goes to infinity, tends to 0. So 2 squared of d minus 1 is as good as you can do. This basically comes from the fact that this is the spectral radius of the adjacency matrix on the universal cover. So this is not some kind of just, silly accident of something. It's really comes from the fact that this is the spectral radius of the adjacency matrix on the d-regular tree. The d-regular tree is, of course, infinite, but if you have an approximate eigenfunction, you can kind of push it down to that of the regular graph. Or you can probably, give the proof that Noga, Alon, and Ratazapana came up with, is just construct something that's a roughly an eigenfunction. But so my favorite paper ever, I would say, is that of Broder and Shamir that gave the first non-trivial estimate of lambda 2. In fact, I'm in my sabbatical project, I'm kind of writing up my recollection. So I remember talking with Noga Alon about a conjecture of his that this is essentially optimal. And I had an idea, and he thought, oh, that's a pretty nice idea. Talked more, absolutely nothing came of it. And then about 2 years later, Andre Broder and Ali Shamir came up with a trace method that I built on. So the theorem, which is due to Broder and Shamir, is about 88, is that if you take a look at the probability, so you take a graph, and they're using the permutation model. And if you look at the probability that lambda of g is bigger than or equal to, it comes out to be 2d to the 3/4, and you take n goes to infinity, and you add a little tiny additive constant here, then this goes to 0. So the lambda is always within, for large d, an amount that is small compared to the first eigenvalue, d. And in a lot of applications, what you needed for network kind of situations was that you wanted that the eigenvalue d to lambda would go to 0. And then you take a sufficiently large d is a constant, you don't care what the constant is, and so on. This is okay, so this is lambda, actually. So they get it from both sides. So So lambda, so these are eigenvalues between d and minus d. I haven't normalized anything. So it says that it's going to be in a small range. Noga. Yeah. So Noga conjectured, and I don't know, I never asked him actually why he conjectured this, but perhaps because of this theorem. So Noga alone conjectured around, I'd say the published versions of these are maybe around 1986 or so. Conjectured that for any epsilon, the probability that lambda of g goes outside of 2 squared of d minus 1 plus epsilon tends to 0 as n tends to infinity. This is for a graph in, well, what was it in? Well, Noga didn't really say. Noga alone didn't say. He said for a random deregular graph. Didn't fix on the model. Today, we'll look at the random permutation model, which is the one that Andre Broder and Elie Shamir used. And he said a random deregular graph. And by the time that I was able to prove this, it didn't really matter what model you used. Yeah. That could be, yeah. So that's a good point. So yeah. Yeah, just exactly 2 squared of d minus 1. So the Cousin-Mackay theorem says that, if Gn is deregular, n goes to infinity, and the number of cycles of any length is small, and number of cycles of length k over n in G for any k goes to 0 as n goes to infinity, then the moments of the adjacency matrix are exactly what would be the moments of the tree. In other words, you walk for length k, from a typical node, and you don't see any cycles, basically. Or the amount of cycles you see goes to 0. So then in any kind of graph like that, you get the rough eigenvalue profile, and it's, as you say, it's precisely between plus and minus 2 squared d minus 1. So that's maybe another suggestion. Next time I'll see Noga, I'll maybe ask him. And then the theorem that I proved is that this verifies the conjecture. So theorem, really, I think I wrote it up around 2002. I waited for a year and a half to get a referee's report, very long report. I do not know from whom the report was. I have my conjecture. It was, I guess, published in 2008, probably in the archive around 2002 or so, that Noga-Allen conjectures holds. So the probability of a graph in G and D of having its, the other thing is trace methods tend to give you information on lambda of G. Lambda 2, yes, but also lambda. This is beginning with 2 squared D minus 1 plus epsilon tends to 0 as n tends to infinity. And in fact, you can get really nice estimates on the exact probability that this doesn't happen, but that's only in the permutation model. And then in other models, can't really say as much. Okay. But my favorite result that really kicked off a large part of my career was the trace method of Broder and Shamir. So this is a good point to stop. So next time I'll tell you what Broder and Shamir's trace method is. I'll explain why they got this bound. Just in case you want another reason to get up on Saturday morning and actually work. So Broder and Shamir next time. So the Broder and Shamir result is essentially 2d to the 3/4. But what they should have gotten, there was never a journal version of their, they kept saying in the journal version, never journal version. They didn't even really recognize the result as this, although everyone who read their paper did. But the result, they made a slight overestimate of a certain combinatorial quantity. The result they really could have gotten was d to the 1/2 times 2 square root of d to the 1/2. What they really could have gotten is the trivial bound to the 1/2, but the conjectured bound to the 1/2. And this comes out of their trace method. And my theorem and methods are based on refining their trace methods. But if you use the non-backtracking matrix, what you'll get is d minus 1 to the 3/4 plus d minus 1 to the 1/4. And if you kind of think of the numerology of this, you've got some geometric mean between these two. And the idea is to get the bulk of it over here. So you want, 1 minus epsilon and epsilon over here. You really want, you want, over here, you really want this to be 1 minus epsilon and this to be epsilon. And then the geometric mean gets as close as you want to 2 squared d minus 1. But this is what you get with the non-backtracking matrix. It is better because this is d to the 3/4 times square root of 2. And this is d minus 1 to the 3/4 times a 1 and something very small. And why this? I mean, it's better than this because of large d it is. In fact, for any d, this is better than this. But why and why this? Well, maybe after next time you can think about it and tell me. because I don't know. Thanks. Yeah, yeah. It is. So if you just want things to go to zero, then it's not model dependent because they're all contiguous. In this model, you can see, what's going to cause trouble. It's going to be, graphs that have, just by chance, a large number of self loops. And these happen with probability and to some power. And that is always the case. Those things will cause the trouble. And when you remove those, the probability of this happening is higher than, it's 1 over n to the c for any c that you want. So you can actually, in their model, it's so nice. And any other model that has the same property that you can get sort of power series for these kinds of events will get you sort of precisely what's going wrong. In the uniform model, I don't know what these probabilities are, or if you can take out, these are so-called tangles that cause the method to fail. I should add that since there are about 3 different proofs of my result, and one of them from Boldenave gives some kind of idea like this. I mean, the non-backtracking and the adjacency, there's a translation. And in the translation, the d of the adjacency goes to the d minus 1, the square root of t minus 1 goes to the square root of d. So it is equivalent. It's equivalent, but when you run the method in the non-backtracking matrix, the result you get is better. Now, if you're going to prove the full conjecture, it doesn't matter, because getting the result in the non-backtracking and adjacency is either way is fine. But for specific estimates, it's better, and I don't know why.